Can you guys see me?
Yep,
Yeah, we
that's
can
fine.
see you. Yeah.
Okay, great. Because I cannot see myself. Oh, yes, I can. Good morning from the United States and good afternoon to you guys in UK and Europe. Just a couple of words of introduction and background to these workshops. And whenever I speak about the workshop, I speak on behalf of my good colleague, Yanis Varna as well. I'm not sure he's attending this time. Few of us, Yanis and myself included, a few years ago, I have forgotten, it's more than 10 years ago, decided that we were not getting something out of the regular conferences that we wish to have, which was to, brainstorm ideas, have discussions, raise controversial topics, learn from one another. Because in conferences, we are typically quite rushed and we make presentations and very little time for discussion. So we began these workshops and we decided to keep them focused around damage of composite materials. So things like damage mechanisms, modeling issues, effect of manufacturing defects on performance, fatigue. Those are the typical topics that we have been discussing. And every time it's been really very intense and I think very giving. Judging from the end of the workshop discussions every time, when we asked, do you want to continue to come to workshops again a year later, it's been unanimous and actually quite enthusiastic support to continue doing that. The last one we had, because of the pandemic, was not there at Imperial, was kind enough to take charge of organizing it. It was an excellent workshop. And here, Michael Wisnom presented some, I would say, questions, provocative questions maybe, about strength of composites. How do we define it? How do we measure it? There was a lot of discussion on that. And it seems that we were not able to do proper justice to that topic because there were so many other things also to discuss. So we pressured Michael to make a special workshop, like this special issue of a journal, right? Focused on strength of composites. So he decided to do that and persuaded Federico to join hands with him. And I think that couple, if I may call them, odd couple, have done a great job in putting together this program. So with that, I would say, I'm very pleased to see that one of the successes of our workshops has been to produce something of this nature where we can, on a smaller but focused topic, come together and in a respectful manner, discuss our ideas, controversies, and disagree, of course, but at the same time in a professional way. So with that, I return myself to the organizers. So Michael, back to you. Thank you.
Thank you very much, Ramesh. So now I'm going to present the paper that Federico and I produced, which has been circulated before this, and Federico will say a few words and elaborate on a particular aspect afterwards. So the question is, how do we define and measure strength of a composite? It's a difficult question and there are many definitions, but the one we proposed was that the strength of a unidirectional composite is the maximum stress that the material can sustain under uniform uniaxial loading. Other definitions really could be much more subjective. And if you take damage initiation, for example, well, it's not very clear where exactly that is, and that depends on how closely you monitor the specimen. So Federico will say a bit more about this later, but if you look at that stress strain curve there, then I think most people looking at this would say straight away it's 550 megapascals, but if you look carefully, you see there's a little glitch at about 380, and where actually the specimen subject to some delamination. So you might easily miss that. If you look more closely, you might see that. If you look with a SEM or CT scanning in situ, you'll see it failing even earlier. And in fact, there are quite likely going to be damage due to intrinsic defects or residual stresses even before you actually put any load on it if you watch it closely enough. In situ strength is another concept, and that depends on many factors. And again, Federico will touch on this in a minute. All these definitions may be useful, in particular in design, but the question is, are they appropriate as basic material parameters? And we argue that really we should go with this maximum stress as the most meaningful strength parameter. Now, there may be considerable damage before you reach the maximum stress. And in the case of this one I've just shown on that stress strain curve, there was large scale delamination. But nevertheless, I think this is valid as a measure of the ultimate material performance. And of course, this can be applied to all the principal failure modes. So let's talk about some of the issues, some of the factors affecting strength. One of the factors which is still not widely appreciated or recognized is the fact that the volume of material tested affects the strength. So you see on the right that there's some results for tensile strength of different size unidirectional carbon fiber epoxy. And you can see that as the size of the specimen increases, then the strength reduces from about 2,800 megapascals down to about 2,400 megapascals. Of course, there are many other factors which affect the strength: strain rate, temperature, moisture. And I think the key point is that these must be specified with a value. Other parameters which can also affect the strength are, for example, the strain gradient. This is particularly important in compressive failure. So on the bottom right, you see a graph of maximum compressive strain at failure plotted against strain gradient from some tests we did years ago using a constrained buckling rig. And you can see that as the strain gradient increases, so does the maximum compressive strain at failure. So we have to be careful to avoid strain gradients, particularly in compressive testing. Of course, it's well known that stress concentrations and other stress components may be present in a test and clearly can affect the result. And you need uniaxial loading and uniform stress, which is easy to say on a slide, but not so easy to achieve in practice. But nevertheless, despite these caveats, we would argue that the maximum stress is still useful to show what may be attained under ideal conditions and as a basis for comparing different materials. There are a lot of challenges in testing composites. Clearly, avoiding stress concentrations and reducing other stress components are obvious ones. And there's been absolutely a huge amount of research on test methods. But I think there's a need to try to synthesize that and to come up with best methods. Despite all the work that's been done by thousands of researchers and all the committees, the ASTM and other international committees, I think there's still a need for more work to synthesize and really appreciate the results of all this work that's been done and try to reach agreement on which are the best methods to use. And of course, testing under combined stresses is even more challenging. And there's clearly a need for more research on the methods and also on what we do with the results, how we use them in criteria to predict failure. Now, when we come on to laminates, it's a whole different question, very much more complex, because in laminates, you have multiple potential failure modes that can interact. You've got transverse cracking and delamination, which can interact with the fiber direction response, especially at the free edge. So this top right shows some results which we did some years ago on different stacking sequences. So these are all quasi-isotropic tensile strength tests of the same size specimens, but you see there's a huge variation in strength just because of different stacking sequences and different ply block thicknesses. So it's not enough to say the strength of a quasi-isotropic laminate because you can get almost any value depending on these different parameters. The presence of other stress components, clearly in a laminate, if the laminate is subject to unidirectional loading, then you've got other stress components in the plies, you've got residual thermal stresses, and you've also got constraint from the other plies And all of these can affect the strength of that laminate. And as an example, on the bottom right are some results for some carbon glass hybrid laminates, which shows that as the carbon ply gets very thin, the constraint of the adjacent glass plies leads to an increase in the carbon failure strain, quite considerable, from about 1.8 up to about 2.2%. So those sorts of effects mean it's very difficult to talk about strength of a laminate because it will depend on so many different parameters. Now, in principle, we could come up with a laminate ultimate strength. We could use tubular specimens, for example, to get rid of free edges. We could select the stacking sequences, the ply thicknesses to try to avoid premature damage. But even if we could really do that, would that ultimate ideal laminate strength be useful? I'm not sure. And I think this is one of the things that is a bit, causes perhaps a bit of confusion is, well, why do we want this strength parameter? Is it to know the ultimate strength of the material and as a reference point, or is it something we want to use in design? And for design, what we need is allowable stresses rather than the ultimate stresses. So sometimes I've heard companies complain about some tests because they give too high a value. So as researchers, we want to know what the ultimate strength is, but actually when you're designing, you want to be conservative and make sure that you're not going to fail it. So I think there's a difference there between allowable stresses and actual fundamental strengths. If you look at things like notch strength, then this depends on all sorts of other parameters. The laminate thickness, ply thickness, stacking sequence, laminate the width to notch ratio, all sorts of additional parameters. And compression after impact also depends on many parameters. So these are useful tests which should give useful information for design, but they can't be considered to be ultimate material tests. They're not generating material properties. They're generating useful values which can be used in designing. And strength of components, I would argue, is a structural phenomenon rather than a material phenomenon. In structures, you've got more complex stress distributions. You may have interaction through thickness and in-plane failure mechanisms. So it's much more complex. So a bit about terminology. Failure strength is quite often used, the term, and I think this is a contradiction in terms, and I think it should be avoided because failure and strength are really opposite sides of that. So I think this is not a good term. It's a mixture really between strength and failure stress. Now, strength and failure stress are often used interchangeably as well, but I think they should be distinguished. I think we should keep strength as a term we reserve for basic, fundamental, unidirectional material strength, and failure stress we use for other cases. So, for example, rather than talking about CAI strength or open hole tensile strength, we should talk about CAI stress or open hole failure stress. It might seem a small distinction, but I think it's important in being clear on our terminology. And of course, we must also specify the measurement conditions under which these have been obtained. So in summary then, we would argue that strength as a material property should only be used for unidirectional composites under simple uniaxial stress states, and that strength should be defined as the maximum stress that can be attained prior to total failure. It should be stated together with the volume of material and the conditions under which it was measured, and the strength should be measured under uniaxial uniform loading. And the results of laminate and structural tests should be referred to as failure stresses rather than strengths. So that's my introduction of our paper. And I'm now going to hand over to Federico, who would like to say a few words and give an example, perhaps to illustrate some of the differences which I've mentioned. Federico, over to you. Federico, I think you're muted.
Yes.
Okay.
Hello, everybody. First of all, thank you for participating in this meeting. And I have also to say that it has been, for me, a nice opportunity to share opinions with Mike, and I have enjoyed it a lot organizing this meeting. I'm going to talk, as Mike has said, about one particular aspect of the topic at a consideration that I had reflected by this expression, strength, damage, or rupture. And I'm going to talk about a particular case, which is the case of one laminate, a typical laminate, the 090 symmetric laminate, and what we typically assign or call scale effect or in situ strength. So if we represent the value of epsilon that produces the failure in general terms as a function of the thickness of the 90-degree ply, we have, first of all, the value of epsilon associated to YT that we have obtained from a specimen applying a uniform distribution of stresses. So additionally, we have another curve significant, which is the energy, the value of epsilon to produce the energy required to generate a complete transverse crack in the 90-degree ply. So, and typically both have been used as complementary criteria to decide what happened in a lamina, or a 90-degree lamina putting in a laminate. So this gives rise typically to the in situ strength, a concept that assigned a value of the strength higher than that corresponding to the value of epsilon associated with YT. But the question is that a couple of years ago, doing some numerical research, our predictions indicated that the appearance of one isolated debonding was not a function of the thickness, which was something that surprised us. So it means that, for instance, if we take a very thick laminate, I mean, a laminate with a very thin 90-degree lamina, we could have at this level of the deformation of epsilon, one debonding, which would be independent of the thickness. So we would have, in accordance with the prediction, the same similar value. In fact, as it is a non-homogeneous material, we would have an interval where this appears. However, when performing tests, the first thing you see of damage, the first thing you see is that indicated here for a very thick 90-degree lamina. So suddenly, with no previous indication, you will have a complete, sorry, I'm going to take the pointer. You will have a complete breakage of the lamina associated with delamination. If now we go to a smaller value of the thickness, we have something similar, but for instance, in this case, without delamination. Even with a smaller thickness, we have something like this, where we have not reached totally the thickness of the 90 degrees, but continue in a similar situation as previously. If now we move to this case, then we have clear indication of isolated debondings. On the left-hand side, the original micrography, on the right-hand side, a recreation to see it clear. So if we have something like this, a thickness like this, we have a situation where we have some isolated debonding may be connected. Now, what happens if we increase the load here? So if we increase the load and move in this direction, then please pay attention to this area as third debonding has appeared, and in other parts of the specimen, we will again have isolated the bonding. But probably we will never get these values because previously the value corresponding theoretically to a total damage, total transverse rupture of the 90 degrees lamina, because probably previously you will have the total failure of the laminate due to the failure of the 0 degrees lamina. So, to conclude, how are we going to proceed? If we want YT to be associated with the appearance of damage, then this value is correct for all types of thickness. If, on the contrary, we prefer, which is the typical approach, to have it associated to the rupture in a general term, probably it would be better to refer this situation as failure stress. And even it would be better to give a designer some indications about values that he can reach, not putting into question the integrity of the laminate. I would like to conclude just mentioning that these are the two papers, one quite recent, that where we have been working on to try to clarify this question of strength related with damage or rupture. Thank you very much for your attention.
Thank you very much, Federico. So now I'd like to invite Ramesh to come back and have his 5 minutes. Would you like to share your screen again, Ramesh?
Sure, will do. Okay, go to full screen mode. All right. Michael, can you hear me or everybody else?
Yes.
Yeah. Okay, great, thanks. Well, what I'm going to say is not really going to be anything new. In the white paper that Michael and Federico put together, you actually have lots of questions, and it's a broad discussion of the strength concept. What I try to do here the next few minutes is to sort of bring focus to the idea of what is actually strength and why do we need it and in what context it is useful at all. So I'll go to the 2 slides that I have. As I say, a picture speaks 1,000 words. So what I have done here is to take 5 typical pictures of how observations of failure mechanisms appear when you take a unidirectional composite and load it in 5 basic modes. So you're looking at tensile mode in the axial direction, compression loading in the axial direction, tensile in the transverse direction, compressive in the transverse direction, and in-plane shear. Now, I mean, you may all know these things, seen this before. If you keep in mind where the concept of strength actually comes from, it comes from metals mostly. And there, whether you load in one or the other way, in any of these 5 loading modes, there's only one mechanism, which is yielding. So initiation of yielding, that we call yield strength, and then ultimate failure that comes from continuation of yielding to a complete failure in one form or the other. But here in composite materials, each loading mode has its characteristic failure mode. Consider the tensile mode. It is highly statistical because it has to do with singlets and doublets and forming of a cluster of broken fibers. Is highly stochastic process. Reverse the loading, and it's much more deterministic, much less stochastic. Failure is totally, of course, fibers have to fail, but they are failing in a very different way in the kink mode. You apply this loading mode, and you, just Federico talked about the issues there. Those are the issues that only arise in this loading mode. It has nothing to do with any of the other 2. If you apply compression, the failure occurs on an inclined plane, which is not at 45 degrees. Then if you do in-plane shear, axial shear, The failure is actually nothing to do with any of the other failure modes. It's not being caused by shear at all. So these cracks that are there, they are most likely because of a tensile stress locally here. Okay, so now we ask ourselves, we follow the tradition of centuries working with metals, and we give designers something that we call strength. What is really, what is the utility of that? So I'm going to take two areas in which we typically want to use the UD composite strength. One is in combined loading. There's hardly any structure that doesn't have combined loading, right? So if I am applying any of those two 5 modes of loading that I described, and I plot one on the vertical, other on the horizontal, and I ask myself, if I combine those 2 loading modes, what's going to happen? Now, our thought process has this legacy of metals where we find that there's a certain, the von Mises criterion gives this sort of a curve. But what probably forget is that it is talking about driving forces under combined loading for one single mechanism, which is yielding. And therefore, a smooth curve like that is expected. Here, what's happening, if I take one of the failure modes here, other failure modes here, they cannot talk to each other at all. Their driving forces are very different. All they can do is, when I do combined loading versus single loading, that the local stress trace and therefore driving forces change. It's not the mechanisms that are interacting. It is just the stress state that is changing. So what can happen is that when I put in this loading mode with its critical value Y to this loading mode, which has critical value X, the value of X is getting affected. I've just done that linear. It doesn't have to be linear. It's often going to be non-linear. Same way here, if I put X, this loading mode on top of the other, it's going to be affected, but it's not interacting. These are 2 different mechanisms. They cannot talk to each other. And we fool ourselves by taking experimental data and just fitting some smooth curve on it. So I will question this idea of using the so-called strength, ultimate strength, like X and Y. All right, let's go to the case that Federico talked about. That is when a unidirectional composite is inside a bigger composite with an architecture, most likely a laminate, but it can be woven fabrics and braided and so on. But I'll take a very simple case of straight fiber laminates. Okay, there the UD composite is inside, right? And we have created lots of different concepts because the basic fundamental idea of strength is really not working out. The failure modes there are taking place in a constrained manner because of the stiff applies on both sides of a UD composite. And there, only one single mode is taking place, which is that of cracking. And it's taking place in a multiple way because of the constraint. So where are we going to use that strength value? It is not total failure of apply. We all know that. Okay, if I also ask myself, well, let's say I focus on the cracking only. So where did I use that X or Y or any of the other values? Because it is not the end of the process. That crack that forms is triggering delamination. How am I going to use any of these strengths that I have of UD composites there? So I had to switch to analysis to another failure mode, which applies to laminates. Then, of course, as Michael was describing in that white paper, size effects and effects of defects and all that have to do with which mechanism is operating and what is its characteristic driving force, which you can talk in terms of energy, which is why I prefer. I think stress is a big mess because it's a tensor and we are dealing with anisotropic materials. So we had to back off, in my view. I'm going to challenge everybody. Back off from thinking like metals and think fresh for composites, use other terminology, use other ways of catching the beast. The beast has many limbs and so on, initiation, progression, final failure. So we need to keep track of mechanisms. Today we can do that and then follow, rather than call it simplistically as strength, whether we use failure stress or whatever, but follow the mechanisms until their culmination to final failure. With this, I'll stop and I thank you.
Thank you very much, Ramesh.
Okay, let me.
Speaker is Hao Cui from University of Cranfield. Hao, I invite you to share your screen. And can I remind attendees, you can put your questions on the Q&A. You can also put things on the chat, but in terms of answering questions, we'll be primarily looking at the Q&A later. So if you've got a question for the panel, please put it on the Q&A. Over to you, Hao.
All right, thank you. Okay, yeah. So here I'm trying to ask a question to all of you. I'm not sure if it's a right question or if it's a right with answer to ask it, but hopefully I hope we can spark some discussion later on, or some thinking about the terminology about strength itself. So here are still two images from Silvestre Pinho, who I saw is here as well, and Peter Comano on two different tests. The first one is like fiber kinking, or the failure of composites in the longitudinal compression. And here, as show very perfectly here, like in a fiber kinking failure, in which we're trying to measure the strength of the composites in a longitudinal compression. And the thing is, the failure here normally initiated by the interfiber shear. And this interfiber shear can happen in a unidirectional compression test because of, for example, the misalignment between, all the fibers against the loading direction. So, this makes me start to asking myself, is this, or is there a true intrinsic strength for composites in longitudinal compression, or rather, it is a structural property even at a unidirectional laminar scale? And the second question is, so here is a transverse compression. We view it probably as one of the simplest experiment to conduct. We take a block and then we do it compression, that's it. And the thing is, if we zoom in and do some in situ test under a microscopy, like for example here we did in SEM, and it's interesting to spot, the debonding between the fiber and the matrix, predominantly because of shear. Why there's shear in this transfer compression? Because when there is transfer compression, there is lateral expansion on the other directions. For example, in the fiber is have higher stiffness in the longitudinal direction, which is where the expansion happens. The same for the epoxy, which will, because of its low modulus, therefore it may tend to expand more. And again, to ensure the continuity in displacement, there need the interfacial shear stress between the fiber and the matrix. So when we look at these two images here, so the question is, fundamentally, is there a valid strength? So, okay, let's say take a unidirectional lamina under a single force, uniaxial force, for example, here. Is this triangle here a valid? Do we have a pure stress? Not sure. Again, as I showed in previous slide, there is, again, maybe let's call it Poisson expansion or, some side secondary shear stress components, which are inevitable. And again, do we have a uniform stress? Not so either, because of, many challenges associated with current experimental capability. And again, of course, before any fracture happens, there is this displacement continuity. So the question is, do we have all these three valid in the same time at a unidirectional laminar scale, or if you're looking further, zoom in at a single fiber and matrix scale? And the thing is, when we talk about strength of a laminate, we have evolved, this homogenization process. So what are the consequences of this homogenization? First of all, we have ignored the edge effect at this small scale. For example, we cannot account for, the shear or any other secondary stress at the edge, for example. And the thing is, how do we have a better idea about, the consequence of the homogenization when, we start from a single fiber and a matrix to a unidirectional lamina, and further to a multi-directional laminate where we can even consider it as quasi-isotropic. So what are the consequences and what are the errors and involved in this whole process? One way I'm thinking is, as many of our partners or colleagues have mentioned rightly, the side effect. As we see a lot, for example, Michael has done lots of work. I mean, many colleagues like Frédéric as well. So the strength changes a lot when the volume of the sample increases. And can we see a similar effect at a macro scale? Hopefully so, because this will help us, to reach a conclusion on how much errors are involved. Because here I see there's a gap. And in the numerical modeling using RVE, where we model each single fiber and matrix, we cannot really go very big. There's a limit in computational resources. And for experiments, we cannot go very small. And there's a gap here. And in this scale, where, hopefully we can, this is where, the side effect or this consequence of homogeneity will manifest. Okay, my presentation will end here, and I hope to discuss you more. Thank you.
Thank you very much, Hao. So our next speaker is Silvestre Pinho from Imperial College. Silvestre, would you like to share your screen?
Yes, I'm sharing it now. Can you all see my screen?
Fine.
Okay, so can you all see my screen? Yeah, okay. So I'd like to touch first on the definition of strength. So if you look at the dictionary, it allows for strength to be used in many areas: strength of coffee, strength of a market, strength of fillings. If we take dictionary definitions that apply directly to mechanics, we have definitions such as power to resist force, the degree to which something is strong or powerful. And so the use of the word strength when referring to the strength of a structure, say a beam, a bridge, an aircraft wing, or even a multi-directional laminate, from that point of view, seem legitimate to me. So the key thing to me, I think, is that strength does not necessarily imply it's a material property. The concept does not come from material science. And so we should, I think, be able to use the word strength without the implication of material property. And so if we apply it to compression after impact or open a hole, if there is no confusion that we are not referring to material property, I don't see from the standpoint of the definition of the word why it doesn't apply. Talking specifically about multi-directional laminates, so one of the things that you were saying before, Michael, that the failure stress depends on the actual layup, that depends on ply thickness, depends on the interaction between failure modes inside the laminate. I agree with all of that. It depends on those things. But if we agree that our material is a specific laminate, then what we are saying is that the strength of that material depends on geometric characteristics inside the material and depends on the interaction between failure mechanisms inside the material. And from that point of view, it seems very similar to what we have in a UD laminate, in which the strength will depend on the diameter of the fibers or the spacing of the fibers or the interaction between the bonds, fiber failure, and matrix cracks. So anyway, so if we turn to UD laminates now, oh, sorry, I was not showing the right slide. So if we look at the different scales, we are focused at this scale here. But I think that if we were to talk to people manufacturing carbon fibers, they might look at our UD plies and think that this is a structure. And so I think people manufacturing beams could say that for them, they want to talk about the strength of a beam as being a limit bending moment, for instance. People looking at graphene, they might look at the fiber as actually being a very complex structure made of graphene. But anyway, if we talk specifically about UD laminates, then I'm not quite clear about what definition of strength and of material properties we should have for the strength to be a material property. So we know, and Michael showed this really well, that the strength as a number, so say 1000 megapascal, depends on the geometry. It decreases with the size of the specimen. So the strength is a property of the material and of the specimen used to measure it. So it's not a property of just the material. And if it depends on also the specimen, is it really a material property? Or should be the underlying properties that define the strength at each different size be what we consider a material property? So for instance, if we agree that longitudinal tensile strength follows a Weibull distribution, then perhaps the parameters of the Weibull distribution would be material properties, but not the strength at a specific size. Anyway, so, or otherwise, we could consider that the strength is a stochastic property, not just a number, and then that stochastic property is defined by distribution. Anyway, there are two things here about this. One of them is when we say, is the strength really a material property if it depends on the geometry of the specimen? Well, we've not defined what a material property is. And I guess the question is, can we define material property in such a way that we allow it to depend on the size of the specimen used to measure it? What definition would that be? And my second question has to do with should the underlying properties define the distribution of the material properties? So if the underlying properties that define the distribution are the material properties, then the strength effectively for a given scale depends on a theory. And so what happens if that theory is not well accepted to explain that failure mechanism? So for instance, for longitudinal tension, I think many people agree that Weibull statistics define well how the strength scales with size for a composite, but other people may disagree and do disagree. Other people may think that in approximation it works reasonably well, but reality is a little bit more complex. So if if the theory is not clear, then defining strength for the underlying properties becomes tricky as well. And so this is what I wanted to talk about. So I'm not exactly in agreement that we cannot use strength in a non-material science context as a summary. And I think that if we talk about strength for a UD ply, then perhaps we are not looking at a deterministic variable, but perhaps at a stochastic one.
Thank you very much, Silvestre. Interesting points you raised there. I'll be very tempted to reply, but we're not going to have questions till the end. So let's move on to our next speaker, who is Tony Waas. Tony, would you like to share your screen, please?
Yes, yes.
Tony's from the University of Michigan.
Yes. Can you see my screen?
Yes, if you want to put it on full screen mode.
Yes, there is. Okay. All right. Thank you. Michael, can you see my screen and hear me well? Okay. Yep. So let's start. Well, thank you for inviting me. Thank you for inviting me, and also for giving me an opportunity to share these slides. I think let's see. I think the previous speakers have very nicely laid the foundation for what I have to say. We've heard some really good remarks from everybody who spoke previously. But here I want to make a few comments sharing my experiences working on this subject for about 35 years now. I think that the Wisnom Paris definition, it is sufficient, but it's very limited, and it's limited to only unidirectional composites. Even then, several factors will affect the definition and the measurement both. And Silvestre alluded to some of those effects, which I like to repeat again. And those are misalignment, packing or proximity of fibers, and details of the Cure cycle, which I haven't heard remarked, but I think Michael touched upon earlier. I can take a UD specimen, I can change the Cure cycle, which I have done, by the way, in my laboratory, and do identical tests and find different values of failure. And the reason is this: the failure of the UD ply is not just a function of the fibers alone, even though the stiffness mismatch is large. It's also a function of the matrix, and the way it sets in is because of misalignment. Small misalignments tend to load the matrix in shear. And what happens is, if you keep loading it, if the interfacial strength or the interfacial toughness is exceeded, what happens is you can get splits. And these splits are energetically favorable because it wants to release the residual stresses in the matrix. That then immediately shifts the load to the fibers, and the fibers can break suddenly because of overload. So the scenario I'm outlining here is one that shows that even for a UD composite, which I think is a structure, even for that, the failure strength, or the definition of the Wisnom Paris definition, can be problematic. Now, can we use it for engineering purposes? I think yes, but just for UD composites. And there are some practical applications of just UD composites in wind turbine blades, in helicopters, etc. For those purposes, I think you can use that definition, but with the caveat that one must understand that this value is influenced by these factors that I just mentioned. Now, extending this definition to laminates is complicated. Consider a very simple case. Let's make a laminate that is plus P, minus P, 0 symmetric, where P can be changed from, say, 1 or 2 degrees to 90 degrees. Let's go to the lab and do the tests, right? Along the lines of what Federico mentioned, let's add also the fact that you can change the ply thickness. So now you have a very rich data set. Now here's the challenge. I only give you Michael's strength value that I measure from the 0 ply. Can you now use that and predict all possible cases of the plus P, minus P, 0 symmetric composite test? Now, it's a challenge. Now, if you do it, and some of us have done this, you will not be able to do it. If you only use the strength, and by the way, like Silvestre said, the strength is a distribution. It's stochastic because the fiber strength is stochastic, and the misalignments and voids and other defects can also be stochastic. The residual stress state is not uniform at all. That's stochastic as well because it depends on the packing. All right. So if you put all that into the question here and consider this challenging problem, you find 2 important things happen. First, you can see that, like Ramesh showed, that the UD composites fail in a fairly deterministic manner, right? You start failure, it progresses, it splits, and then the fibers break. You can see that with the pictures. But you'll be surprised if you go and look at how the 0 fibers failed in the plus P, minus P 0 composite, you'll realize it's not the same as when it failed in the UD composite. In fact, in some cases, the 0 ply crack the breakage is influenced by the adjoining minus P ply. In other words, if minus P is at 45 degrees, you may find that the 0 also failed close to the 45-degree line to the loading direction, suggesting that there is influence from other plies. Okay, so it's very important. Failure modes are changed. All right, finally, what I captured there in my previous comments is basically captured here. three things I want to say. First, the manufacturing process is important. It can influence the values we measure. So laminar strength is a complex quantity. I have already made that point. Okay. Second, we must do scale-dependent experiments. The speaker from Cranfield said the same thing in a different way. We must have scale-dependent experiments, and there's a gap, right? You can do very small simulations at the nanoscale, but it's difficult to do experiments. You can do experiments with larger specimens, but then simulations won't help you that much. Finally, we must define homogeneity. If I want to really go back to Michael's definition, we must define what do we mean by homogeneity. It tells you clearly, when you start thinking about it, it tells you the length scale you're operating in. Homogeneity is a length scale definition, in my opinion. And so with those comments, I'll stop there and I look forward to listening to everybody else. Thank you.
Thank you very much, Tony. Our next speaker is Kwon from the Naval Postgraduate School in Monterey. Yang, you share your screen, put your camera on, please.
Yes. 1 second. Oops. Good morning. Can you hear me?
Yes.
Okay. So good morning, good afternoon. And so before we talk about, the definition and measurement of strengths of composite, I'd like to see and then what really, contribute to the strengths of composite. Since composite is made of, fiber and matrix material, so I'm going to talk about the composite strengths in terms of the perspective of constituent material. So as you know that, composite is made of fibers and matrix, or sometimes you call particle if the fiber is going to be short and the same dimension, almost same dimension in every direction. But anyhow, so those are two the major material, making a composite. And of course, we are talking about the long fiber composite, but it could be short fiber or discontinuous fiber, or sometimes woven, the fabric composite. But in any dose of composite, if you look at the failure at the constituent material level, such as fiber and matrix material level, then we can say that those failure could be classified into three different modes. One is the fiber failure, and second is going to be the matrix failure, and the last one is going to be fiber matrix interface failure. So, for example, if you apply that, the loading along the fiber direction for unidirectional composite, then mostly the matrix failure is going to initiate, followed by interface failure, and then eventually fiber failure. On the other hand, if you apply, the load to the transverse direction of the fiber, then fiber doesn't fail, but matrix and interface are going to fail. And even the delamination is also the matrix failure and or the interface failure. So anyhow, those failure modes can be simplified in terms of those three, basic failure at the constituent material level. And also, if you look at the failure of the unidirectional composite on the tension, then we call, fiber is going to be the fracture eventually. So this is that, we can say material strength of the fiber. However, if you look at the, the unidirectional composite on the compression, then as you already saw in some of the fiber kinking in the previous, the presentation. So those are not actually the material strength, and those are the, instability problem. So that in terms of the micromechanics, that the fiber buckling is not the material property rather than structural instability problem. And then going to the second question, what really influenced the composite failure and eventually the strength of the composite? Then there are many parameters, influencing those failure mode and failure strength, etc. But some of them are controllable, and others we cannot control, unfortunately. So, of course, the most significant, the parameter is going to be the selection of fiber and matrix material, and those we can control, and also their volume fraction. And that is going to be one of the main, the parameter defining the failure and strength of that particular composite. But some other parameters, such as the shape, size, and more importantly, as also discussed in the previous presentation, is going to be non-uniform distribution of fiber and fiber misalignment. Unfortunately, we cannot control those that well. And also, depending on the curing process and also the material, fiber matrix interface condition, those are also we cannot control that well, and we have to accept as it is after the curing process. And also there are some initial damage, such as that micro void or some debonding between the fiber matrix during the fabrication process, and those are going to also affect the failure too. And another one is going to be, for example, thermal residual stress during the fabrication or during the change of temperature with the constraint of in the layer of the laminate composite. For example, when you have the unidirectional composite without any physical constraint and then subject to temperature change, then at the composite level, because there is no physical constraint, there is no thermal stress, and there is no stress. They are free to expand or contract. But at the constituent material level, fiber and matrix, there are thermal residual stress because of mismatch of coefficient of thermal expansion. So this one, show that in simple analytical unidirectional model, when you have a fiber matrix and then 50% fiber volume fraction of temperature change 100 degrees, then this example showed that the fiber is subject to tensile stress, and then matrix has subject to compressive stress, and also stress is going to be different depending on the orientation of that this one. So definitely those thermal residual stress are going to affect the failure of composite. And even Tony mentioned that if you have the layered composite, then also each layer constrain each other, so that there is going to be the additional residual stress during the fabrication process. So all those parameters are going to affect that eventually failure of composite strength. So what I like to state in here is that when you look at the failure of composite, we need to also look at the failure in terms of more physics basis, which are going to be that at the constituent material level. So hopefully we can have better definition and try to measure strength of composite. That's it. Thank you.
Thank you very much, Jan. Our next speaker is Soraia Pimenta from Imperial College. Over to you, Soraia.
Thank you, Michael. Give me just 1 second to share my screen. Can you see my screen, Michael?
Yes.
Okay, perfect. Then I guess that's everyone else will also be able to see it. Good afternoon, everyone. Thank you very much to Michael and to Federico for organizing this workshop, and also for allowing me to have a time slot. So as you can see here, I'm going to talk about a slightly different material from the ones that we have been focusing on. So I'll be talking about discontinuous fiber composites rather than continuous fiber composites, not because they have particular challenges that are not seen in continuous composites, but because they do exacerbate some of the challenges that we also see in continuous composites, and that are common to, I believe, all types of composites. Okay, so those challenges, I think, can be divided into three categories. So the first one relates to the heterogeneities that we have in the material. So the image here on the top left shows the microstructure or the mesostructure of the type of materials that I'm talking about. So the reinforcement is based on toes of unidirectional composites that you can see here can go up to 50 millimeter long and 10 millimeter wide. And this means that we have a material which is heterogeneous at quite a large scale. Now, the image that you are seeing actually represents the gauge section of the specimens that we have used before to measure the strength, let's call it that, of these materials. And you can see that clearly we have a microstructure that interacts with the scale of the geometry. And for instance, if we think about ASTM standards for testing the tensile strength of composites, and in particular the tensile strength of discontinuous composites, they actually recommend that we use only half of the width of what we have here in this specimen. So the fact that we have a microstructure which is heterogeneous at such a large scale means that the geometry of the specimen that we are testing definitely affects the failure process. So you can see here in the plot below that if we test specimens with different widths, by changing the width by a factor of 4, you can easily increase the strength of the composite that you are measuring by almost a quarter, which is something that we have also seen in Michael's presentation happens for continuous composites, but it is a much stronger effect that we see in this type of discontinuous composites. And one of the main reasons why this happens is because at the scale of the reinforcement, we don't have an homogeneous and we don't have a uniform stress field. So each toe is going to see a completely different stress field in its own coordinate system. And we also have a stress field which is not uniaxial. So a second challenge that we have is the influence of the manufacturing process on the properties and on the microstructure of the composite. So we have heard other speakers before mentioning this problem, for instance, when we try to measure the compressive strength of composites. For discontinuous composites, again, this becomes, I think, a much more severe problem because you have a huge amount of flow of the material during the manufacturing process. So, for instance, if you try to manufacture a T-joint as the one that you can see here, you can see that from process simulations, we basically have different alignments of the fibers in different points, and therefore we are going to have necessarily different mechanical properties at different points. And the thing that I think is key for this type of materials is that you have a continuous range of different fiber properties due to the different fiber alignments just in this very small area of a specimen. So, for instance, while in a quasi-isotropic laminate, as we have talked about before, you would have discontinuous ranges of fiber orientations in the different plies. In discontinuous composites, you actually have a continuous range of the expected layups or the expected fiber orientations that you have at each point. So in this plot below, you can see some measurements that were done for discontinuous composites with different types of fiber alignment. So going from the fibers more aligned with the loading direction in red to the fibers more aligned with the transverse direction in blue. But we basically have a continuum of different properties in between these three columns. So there is no reason to say that this red column is more important to characterize this material as a column that would correspond, for instance, to the yellow color in the specimen that we have here at the top. A third challenge that we have, and this is something that, again, other people have mentioned before in the scope of continuous fiber composites, is stochastic variability. So the plot that you can see here on in the center shows the expected fiber alignment from process simulations, but actually you will have a significant amount of variability of the actual fiber alignment of the actual toe layups that you have in a given specimen or in a given structure. And this raises a very odd behavior of these materials. And for instance, if you drill a hole in your specimen might not fail under tension at the cross section of the hole, but it might fail somewhere else. And for instance, if you plot the total load that your specimen can take, or the gross strength of the specimen, so normalized by the gross cross section of the specimen, we would expect from classical solid mechanics that any material would fall below this perfectly plastic or notch insensitive line. But we actually see that in this particular case, for this particular discontinuous composite, it's actually less notch insensitive, or more notch insensitive than a perfectly notch insensitive material, which is something that cannot be understood using any classical solid mechanics theories. And then this goes a little bit in line with the problem that that Ramesh highlighted at the beginning, where he said that we cannot necessarily use concepts that were developed for metals and apply them directly to composites. So what I would like to discuss now is not the reason why this behavior appears. We understand that, we can even model it, but to actually think about whether we can use some of the discussion that we are having in this workshop, mostly for unidirectional composites, and apply it to other types of composites. And the first thing that I would like to think about is why do we need to define strength? So several other people highlighted that it's important to understand why we want to define strength. And I think that one of the reasons is to guide the material selection and to guide the development of new materials. So if we want to compare a material against another one. So for instance, I have now added the gross strength measured for different hole diameters, not only for a discontinuous composite, but also for a quasi-isotropic continuous fiber composite. And if I want to compare these two materials, for instance, should I say that my discontinuous composite is it 60% weaker than the continuous fiber composite? Or is it about 20% weaker than the continuous fiber composite? The other reason why we might want to define strength, I think, is to guide the design of structures. So where we basically want to identify what is the critical value of the loads that we can apply to that structure. And taking those two goals into account, the question that I would like to pose to you is whether we can adapt the principles that we will hopefully agree for UD composites to non-UD composites. So a first question is how uniform and uniaxial does the stress need to be? And at what scale does that need to happen? Do we think that strength is still okay when it depends on specimen dimensions significantly? So you have seen before, just by increasing the width by a factor of 4, you get an increase of the strength or a decrease of the strength by almost a quarter. Is it still okay in this case? How can we define a basic material parameter, which is something that Michael and Federico's document highlighted that we should identify when we have a continuous range of fiber orientations and when we have several interacting failure mechanisms, so we don't have a separation of failure mechanisms anymore? And is notched strength not okay, even when a notched specimen might have exactly the same failure mechanism as an unnotched one, and even the same remote stress? And finally, when is the definition of strength meaningful? So in my opinion, it needs to be unambiguous. And this is when having standards and defining exactly the conditions in which we measured that strength is important. And in my opinion, as long as we define a strength unambiguously, and for each material we can have many definitions of strengths, and for each structure we can have many definitions of strengths. As long as those definitions are useful, and I say useful either to compare different materials or to help us designing structures, I would say that any definition of strength that fits those two criteria, so unambiguous and useful, is a measure that we should probably use. We can call it different names, but it's something that will help us to make better materials, to understand better the materials that we have, and also to design better structures. And this is all from my side.
Thank you very much, Soraia. I'd like to now introduce my colleague, Stephen Hallett from Bristol Composites Institute, our next speaker.
So good afternoon, everybody, to those of you in the UK and local time zones, and good morning to people elsewhere in the world. Let me just start to share my screen. Is that good for you, Michael?
Yep, it's fine, thank you.
Okay, so I want to particularly focus on moving up the length scales. We've heard quite a bit about sort of some of the micromechanics and micromechanisms that go into to contribute to material failure and the definition of strength. We've heard arguments both for and against, or challenges for, in this arena at that length scale. But I perhaps want to pick up and focus on Soraia's one of Soraia's definitions of useful strength. And so let's assume that we actually get to that point where we've got a useful strength value for a given material, and then look at, well, how do we actually then translate that into structural scale failure? First off, I'd say failure is a very subjective thing when it comes to structural level. It can mean first ply failure, if perhaps one's looking at something like a pressure vessel, whereas in other applications it can be a percentage stiffness loss. So perhaps just as difficult to define as strength. But again, let's assume that we we know what our definition of failure is, and we've got a good understanding of what our material strength is. That doesn't mean we're out of the woods yet, as it were, because there are still plenty of additional challenges when it comes to then making use of that strength. So I just want to particularly touch on a few different cases from our work at Bristol, where variable effects can be observed, particularly as one moves up the length scale. So if one looks at laminate or coupon level tests, I've got two examples on the screen here, both of which have localized stresses. On the left-hand side, it's a multi-directional laminate where locally one gets a bit of surface matrix cracking, and that surface matrix cracking leads to some small corner delaminations at the intersection between that matrix crack and the free edge. And as you can see from the FE analysis, we get a local stress concentration, and that stress concentration is actually then becomes high enough to influence the overall failure of the specimen. And if we look at the net section stress from classical laminate analysis and our useful strength, we'd actually overpredict what is the measured strength. So we really need to understand the mechanisms and their interaction. And again, I think that this has been touched on by several speakers already. On the right-hand side, we've got a different case where we've got a much higher stress concentration from a sharp notch, which leads to some local blunting due to some damage. And what you'll also see is that the crack is starting to propagate. So we have now exceeded the material strength, but in this case, we've actually got a case that local failure does not lead to a catastrophic failure, and the specimen is able to continue carrying load and will reach a level above that of the very localized material failure. So it is, as we move up the level of complexity, the failure of a specimen becomes very dependent on the local conditions prevailing, the local geometries, and the interplay between the different damage mechanisms. Going even further to more structural level loading, so where we are looking at more complex geometry and stress states. So we measure stress in, well, measure strength in, as Michael and Federico suggested, in a unidirectional stress state, but at a structural level, we are more likely to encounter multi-axial loading. And the bottom left chart shows that some tests we did where we have a specimen loaded in tension, but with some applied highly localized compressive stresses. And what you see is that the measured longitudinal stress in the material drops off with the applied pressure. So again, we need to not only understand the local damage interactions at play, but also the multi-axial stress state. And finally, want to just look at also the geometric effect, again, as we go up the length scale. So again, if we refer to sort of lab scale tests, we tend to use quite simple specimens, and this looks at an example of a compression failure of a laminate with a wrinkle in it. And in the lab scale specimens, we would tend to make that prismatic, which in turn will lead to a very catastrophic failure, which you can see from the photographic image on the right. However, if we translate that again into a real world structure, that wrinkle or waviness is likely to be quite localized. And what we tend to then see is a weakening or damaging of that material, a loss of stiffness, and a load transfer elsewhere. And so actually our structural failure tends to be in perhaps the less wrinkled material that ultimately starts to carry more load as we get transfer of the load path. So I guess in summary is really raising a few questions and putting a few examples up of the complexities of using strength values, but also that, I guess, an indication of the way forward where a real profound knowledge and understanding of the failure processes can start to make use of some more fundamental material properties, which, although not perfect, can still be very useful and effective in an engineering sense.
Thank you very much, Stephen. So we now move into the final section on measuring strength. We've got 3 more speakers. We are running a bit behind, so if I can ask our final speakers to really try to keep to time, please. And our first one in this section is Lars Mikkelsen from the Technical University of Denmark. Lars, over to you.
Can you see my screen? Also,
yes, that's fine. Thank you.
Yeah. Just want to. Yeah. So I will actually go down to a very simple case. So finding the tensile strength of a UD homogeneous distributed carbon fiber composite. So this is a prepreg. We have 2 studies, one of a prepreg carbon fiber composite and one of a pulsed profile. So you can see the structure is rather uniform, and the color codes here is indicating the misalignment going from 0 to 5 degrees. So also the alignment is really, you would say, well aligned composite. There's a prepreg, so we have, say, a layer structures, which you may be able to see here. So we have tested that this sample, put up more and more layers from 3 plies to 10 plies, and then use 3 different geometries to test that. And if you take the rectangular test sample first, that is the red columns here, and when we have the sample get thicker and thicker, we have more and more plies, then we can see at a certain point, then our strength of our material will decrease. Actually, we can calculate or see that we go from that is a constant stress value that until it is constant load values, indicating that is something described by a load which are during the failure, and that's probably some, or we can see it's outside the gauge section, the failure which are happening. This is mechanical grips for this case here. Then we can try to make other geometry. So this is this butterfly shaped sample we are using a lot for also fatigue test. If you do that, that's the green points here, or green pillows here, and we can see that again we have a constant value, but then again if you come up to the thickest one, then you also get a decrease in that value. Then we can say, okay, then we may even do a more elongated butterfly shaped sample here, and for that we can see that now we are be able to keep this high value for the thickest one, which are this 5.5 millimeter. But this indicates that we can use, if it's possible to make the same composite but thicker and thicker, then we may indicate whether the failure described by the thickness is controlling our test sample. So in some way, this is a way to investigate what is controlling the failure of our test sample. It may be difficult to see on the failed sample. So what is the reason for this? If you do a simple stress analysis of the 3 geometries here, then the blue curve here is corresponding to the rectangular sample, and the green curve is to the long butterfly sample. We have some stress intensity. So this is the normal stresses in our sample. So we have some stress intensity where we have the end of the tap material. For the other 2, we have tapered tap material here going from 2 millimeters thickness down to 0 thickness here. And we can see there's also some stress intensity here. smaller for this one. I have here shown the normal stresses just below the surface of our test material. But what is more critical, I think, is that, so here this is a stress value. If you look at the shear stresses at that region here, the dashed line here is the thick one and the solid line is the thin one. You can see that we have rather high shear stresses near the end of the grips. And that's for all cases, so also for the butterfly and for the X butterfly, we have larger shear stresses because that's the only way we can introduce the load from the grips into the test material. So it may, and we can see that the load levels for the shear stresses are quite high compared to, I would say, expected shear strength of the composite. And here is indicating, showing the failure of this composite here. So you can see this a lot of fiber failure and splitting of the test sample. So it can be hard to identify where the failure happened. For the thickest one, we can see that we have this shear failure between the tap and test material, and we also, for the butterfly shape, we also have splitting along the UD fibers. So this is for the pre-preg carbon fiber composite. But we have done a similar study for the protruded carbon fiber composite. For that, we cannot vary the thickness because that's given by the protrusion profile or the protrusion process. So here we have a 2 millimeter thick sample again, or even more. Here we have a case where we have rather uniform distribution of fibers, very aligned fibers. So here's this fiber orientation efficiency factor, which we can calculate. So that's reduction, which are corresponding to, you could say, the misalignment of fibers, which is very small here. And we also, for this, have even a higher fiber volume fraction. For the pre-preg, we have 60, but here we have, what is my point? Okay. And here we have 67% fibers. This is a rectangular sample. So where we can do the, you would say, tensile test. Then we need to have, I'll come back to that, the reason for that, how to define when the fiber, the composite is failing. So here we would like to talk about strain to failure. And here the strain to failure value is defined as the point for max stress, but where we are ignoring this, you could say, local failure happening before the max load point by doing a polymeric fitting of our tensile curve. So this test here is then going to one line here, and then we have the scatter of the different samples and the mean value of the stress strain curve. We can then, inspired by Wisnom and co-workers' work, we can now do the same rectangular sample, but now with a reinforcement layer, or we are replacing the tap material with a ply of glass fiber and make this as thick such that it will survive the failure of our test sample. So now this is a green curves here, where we here have the stresses of the complete test sample. But then if we subtract the glass fiber effect, then we get the stress value in the carbon fiber. The strain to failure, we just take the values here and put over here. So we can see that the strain to failure is larger for the case where we have this constraining layer on both sides of our protruded profile. Now we could try to do that also for the butterfly shape, and here I only show the results for the extra long butterfly shape. So this is the same shape as before, but now again here we have put a constraining layer on top of the material, which are so thick so the sample will survive the failure of the carbon fiber. And now we get the purple lines here, which can, and the purple and red line here. So the red is for the constrained case, and the purple here is for without any constraint layer on our extra long butterfly sample. And we can see over here that for the constrained version of the butterfly, we even get higher values here, so indicating that we may be closer to the true strength of this the protruded carbon fiber. But how close we are is actually a good question. You may say that this could be due to a scale effect of our composite. We know that there's a lot of, you could say, size effect in the fibers, and we have tested that and find the variable exponent n value equal to 7. But for the composite, the question is what is for the composite, the question is what is
I think we need to finish there anyway, Lars.
Yeah. So I'm sorry, it's my Google Home which I begin to play in the bottom. Okay. But the size effect will only could say take into account 1/4 of the measured improvement of the strength going from the rectangular sample to the butterfly sample. So that's is in short the conclusion from the size effect. Okay, so
thank you very much. So that's very good. We'll now move on to Yentl Swolfs from KU Leuven.
Thank you, Michael. Can you hear me?
Yes.
Okay, I will start sharing my screen. Can you see my screen?
Yes.
Okay, thank you, Michael. So I want to talk about proper tensile testing of UD composites. So this is very much in line with what Lars was just presenting. But I want to start off by saying that I think if you look at the literature and all the tests on pure UD composites in the fiber direction, I would argue that 95 to 99% of that data is actually not reliable. And I hope that you will be at least somewhat convinced of that when you see some of the results I will be presenting. So we did a range of tensile tests on UD composites, and here we used HS40, which is a relatively brittle carbon fiber with a failure strain of 1.05% according to the data sheet and a stiffness of 455 gigapascal. We put end taps on this, and this is just standard E-class epoxy cross-ply laminates. And we did 6 different configurations, which are schematically shown here. So we used the default approach, where you don't have any end taps. You use just the normal end taps that are with the 90-degree corner essentially here. Then we had the tapered design, which some people believe gets you slightly better results than with the 90-degree corner here. Then we used the continuous end tap design developed by Michael. We did something similar with the butterfly design as was presented by Lars. And then something that was a little bit more exotic that you don't see that often in the literature with arrow-shaped end taps. So these tabs are designed in such a way that here the length from this part of the tab to that part is always equal to 150 millimeters. So the volume we're testing is the same as in some of these other specimens, apart from this where the gauge volume was a little bit different. So if we first look at the first 3 types of specimens, we are plotting the results here in terms of failure strain, which has to do with the continuous end taps where we cannot measure strength directly. So if you look at the failure strain and you compare it to the datasheet value that I mentioned, then you actually see that for the pure UD, where you do not have any end taps, you actually, if you would rely on this value, which would be a significant underestimation. But also if you do add end taps, either with the straight edge or the chamfered tabs, you would still be underestimating the datasheet value. Now, if you would analyze the continuous end tab design, then you actually get pretty close to the datasheet value. A few things important to point out here. Our plies were well above 100 micrometer, which means there is no hybrid effect, at least if you correct for the thermal residual stresses. The difficulty is that this is actually not a technique that you can directly measure strength, because that strength requires a back calculation, which introduces some additional error. So that's why it's better to look at the failure strain in interpreting the data from this type of specimen. The great thing about this test is that you know where the failure happened, and most of the time that actually happens away from the end taps, nicely inside the gauge section. And that is a big problem with all the other specimen designs, for which if you don't know where it failed, you cannot know whether that particular test was a reliable test, because you don't know whether it failed under uniform stress conditions. So then we had big hopes for the butterfly design, but unfortunately this was in some regards the worst test, in the sense that this gave us the lowest failure strain. And I think that is an indication that this was not a very good test, at least not for this specific material. I should also point out that this was the only test that had a smaller gauge volume, which you would actually expect to lead to a slightly larger failure strain or strength. And lastly, we tested the arrow-shaped end taps, and they actually led to pretty good results that are quite well in line with the continuous end taps. But the benefit being here with this one, you can actually get strength directly, but we don't know whether the specimens actually failed in the gauge section. So this is certainly an interesting design to look at in further detail, because this is also much easier to use than these arrow-shaped tabs, than the butterfly design or the continuous end taps, where you need to either water jet or add glass plies on top and then do a back calculation. So I think with this new design, you can actually do quite easily reasonably reliable results, but ideally you still would use, for example, a high-speed camera to detect where failure happened, so that you can throw out the samples that did not fail away from the grips. And with that, I'll leave you to it, and thank you for your attention.
Thank you very much, Yentl. So our final speaker is Frédéric Laurin from ONERA, French Aerospace Lab. Frédéric, tell us about compression.
So can you hear me and do you see my screen?
Yes, thank you.
Great. So good afternoon, everyone. I'm going to talk about the analysis of different tests in order to determine the longitudinal compressive strength of unidirectional ply. So the idea here is to present you the different available tests to measure a strength defined at the mesoscale, at the ply scale, in order to determine the longitudinal compressive strength, which is associated to the fiber kinking, which has been presented many times before. So I'm going to talk about the tests that you can perform to determine such a quantity. So you can first perform a standard compression test. You can find here the reference of different standards that you can find in the literature. The major difference between such a test is the manner that you are going to transmit the compressive force into the specimen. You can use, for instance, you can introduce the loading through end loading. You can introduce the load through shear loading, or you can perform a combination of two. At ONERA, we have performed such a test on carbon epoxy composite materials, which is T700 M21. We have performed compressive tests introducing the compressive load through end loading. The test is pretty easy to perform, but you are going to observe that the failure often occurs close to the jaws. It has been clearly explained previously, because at the end of the jaws, you are going to generate in-plane shear gradient, which are going to interact with the longitudinal compressive stress and induce premature failure at the end of the jaws. Therefore, you are going to obtain a pretty large scattering. In that case, the covariance of the test was around 10%, which is pretty high. Moreover, because the failure occurs close to the jaws, most of the time you are going to obtain pretty low value of the strength. In that case, it is around 900 MPa. So the idea is to propose a test in which we better master the boundary conditions that we are going to apply to the specimen in order to measure the strength. So you can do that considering bending test, because for lots of carbon epoxy materials, the longitudinal compressive strength is 2 times lower than the longitudinal tensile strength. Therefore, you can perform a 4-point bending test. The point is that most of the time you are going to obtain premature failure under the loading span. This is the reason why at ONERA we have proposed a compression with pivot device test. So such experimental device allows to generate bending loading by offsetting the midplane of the laminate with respect to the rotation axis of the pivots. If the off-axis through the thickness is equal to half of the total thickness of the laminate, you are going to generate a quasi-pure bending loading. Therefore, this test is pretty easy to perform. It's just a compression test with the pivot. And a good point is that you are able to measure the strain on the 2 faces during the test pretty easily if you use, for instance, digital image correlation. You can also observe, as it has been mentioned previously, where the failure occurs, which in that case, the failure occurs far from the jaws. So that's a pretty good point. But if you observed precisely the failure patterns that you can see on this slide, you can see that through the thickness, you can observe 2 different failure mechanisms. One is due to the fiber failure in compression, and one is due to the fiber failure in tension. And you can see that it is really challenging to predict the ratio between the competition between these 2 failure mechanisms. Therefore, such a bending test, in my opinion, should be considered as a validation test for advanced damage and failure approach instead of an identification test. And to finish, I'm going to present you a test which is really dedicated to composite materials. The idea is to perform a tensile test on a laminate with a very specific stacking sequences in order to measure the compressive strength. The main idea consists in testing a layup containing a central 90-degree ply. Due to Bloch-Poisson effect, you are going to generate longitudinal compression into the central 90-degree ply. And using an optimization algorithm, you can define the orientations of the other ply around in order to avoid any damage prior to the final failure, which is due to the longitudinal compression of the central ply. So we have applied such a strategy to the T700 M21, and we have observed pretty nice fiber kinking into the specimen. You can see here what we have observed using CT scan or SEM observation. We were able to measure the average strength, which is pretty high, minus 1000 MPa. But the point which is really important is that the scattering associated to such a test is very low. Why? Because in fact, the maximum strain and the maximum stress are located at mid-width of the specimen, far from the edges. Because in fact, the loading is introduced through blocked Poisson effect. So because we are far from the edge, the scattering is pretty low and close to the real material scattering of the material. So that point is very important because what we want to do at the end of the day is to transfer our methodology to our industrial partners, and they are going to use allowable, it has been mentioned by Michael Wisnom at the beginning of the seminary. So if you want to develop a test which could be transferred to industry, you have to fulfill 2 different criteria. You want to obtain the highest average value, as it has been presented previously, but you have also to consider the fact that you want the lowest scattering associated to such a test. In other words, it means that you have to master or at least control the boundary conditions that you are going to apply to your specimen. My last comment concerning the compression test is really dedicated to the fact that it is a material strength or not. You can see that the strength associated to the bending is higher than that measured considering an in-plane loading. And it is find in the literature also for many other carbon epoxy materials, because the fiber kinking is really associated to fiber microbuckling, which is not a material mechanism, but as it has been mentioned previously, an instability phenomenon. So we have to think about the choice of the scale we are going to consider for the modeling and for the analysis of the mechanism, especially for compressive loading. Thank you for your attention.
Thank you very much, Frédéric, and thank you very much to all of our speakers who've given us a lot to think about. We have overrun a little bit and we want to have time for discussion. So I think we'll just take a 5-minute break now and we'll start again at 5 to whatever the hour is, wherever you are. So thank you very much. We'll see you in 5 minutes.